In this mini lecture, I'm going to talk about geometric sequences. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. Obviously, multiplying by 0 wouldn't lead to a very interesting sequence. We'd start with 4, 4 times 0 is 0, 0 times 0 is 0, 0 times 0 is 0. So the constant can't be 0. The amount we multiply by every time is called the common ratio of the sequence. So if I specify a first term, a sub 1, and a common ratio, r, then this determines a unique geometric sequence. And we can say that a sub n, the next term in the sequence, or the general term, is a sub n minus 1. That's the preceding term times r. So we take the term before, we multiply by r, that gives me the next term. So, example 1 here, write the first 6 terms of the geometric sequence with the given first term and the common difference. So a sub 1 is 3, we've got r is 2. If I let n equal 2, we get the a sub 2 is a sub 2 minus 1 times r. So that would be a sub 1 times r. So that would be 3 times 2, or 6. So my first term was 3, my second term is 6, and of course to get there I just multiplied by 2. So I just multiply by 2 again. 6 times 2 is 12. Oops. I just keep multiplying by 2 every time. 12 times 2 is 24. 24 times 2 is 48. 48 times 2 is 96. So those would be the first 6 terms of that geometric sequence. In part B, we start with 72, and then I have to multiply by negative 1/2. Of course, multiplying by a half ends up being the same thing as dividing by 2. So I start with 72. I multiply by negative 1/2, or divide by negative 2. That changes, of course, the positive to a negative. So I go to 18. When I multiply by negative 1/2 again, negative times negative is positive. 36 over 2 is 18. Then I divide by 2 and get negative 9. Now, again, if you're unclear, we get negative 9 times negative 1/2. That would be positive 9 over 2. And then we'd have positive 9 over 2 times negative 1/2, which would be negative 9 over 4. So those would be the first 6 terms of that geometric sequence. The common ratio can always be found by dividing any term after the first term by the previous term. And although any pair of terms will work, you can always just divide the second by the first if you want. So we see here in part B, the second term is negative 36, the first term is 72, and when I simplify that fraction I get negative 1/2. Or here, r would be 6 over 3, which is 2. So that's just how we can find a common ratio if we're given a sequence. Okay, let's go to the next page. So let's say we have a geometric sequence. We start with first term a1. We have a common ratio r. So a1 is just a1. A sub 2 would be a sub 1 times r. A sub 3, the third term, would be the second term times r. But the second term is a sub 1 times r, so that goes in here. And then the third term is a sub 2 times r. That goes in here. And we see what's happening, right? So a sub 3 is a sub 2 times r. A sub 2 is a sub 1 times r. So I get a sub 1 times r times that other r. For a sub 4, that would be a sub 3 times r. I guess the problem here, oops, went farther than I wanted. So yeah, this a sub 1 times r goes in for a sub 2. So that's where that goes right here. For a sub 3 is equal to this. So that goes in for a sub 3 in those places. And what happens then, every time we're just multiplying by another r. So I multiply by r once, I multiply by r twice, I multiply by r 3 times. If I want to get to the sixth term from the first term, there's 5 terms I have to make up in between there. So I have to multiply by r 5 times. And if we look at this, the exponent on r is always 1 less than this subscript. Right? A sub 3 up here is a sub 1 times r squared. So a sub 3 in r to the second. And a sub 6 is r to the fifth. So in general, a sub n, we have a sub 1 times r to the n minus 1. It's always just 1 less. So here, in this problem, we've got that a sub 1 is equal to 5, and we've got our common ratio is equal to 3. So a sub n is a sub 1 times r to the n minus 1. If we want the 8th term, we're plugging 8 in for n. So we get a sub 1 times r to the 8 minus 1. So a sub 8, a sub 1 is 5, r is 3. So I get 5 times 3 to the 7th. If I take 3 to the 7th power, you might use a calculator to do that. That would be 5 times 2187. And if I multiply that, I get 10,935. And again, that's a sub 8. Oops. No. Next page. Go to page 3. Here we go. So here, I've got that a sub 1 is 32,000. And we've got that r is negative 1/2. So we know a sub 1, a sub n is a sub 1 times r to the n minus 1. So if I want the 10th term, I'm going to plug 10 in for n. So that's going to be a sub 1 times r to the 9th. A sub 1 is 32,000. And we're going to get negative 1/2 to the 9th power. So negative 1 to the 9th is negative 1. What's 2 to the 9th? 2 to the 9th ends up being 512. So we get negative 32,000 divided by 512. I can simplify that fraction, or I can just see what happens if I divide that on a calculator. And we end up getting negative 62.5. Okay. So that's finding an individual term in a geometric sequence. We're also sometimes interested in adding up terms of a geometric sequence. So if we have s sub n, that would be a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. Now, here's some calculation. So s sub n is going to be a sub 1 plus a sub 2 all the way up to a sub n. Remember though, a sub n is a sub 1 times r to the n minus 1. So this right here is a sub n. Right? So this really is a sub 1, this is a sub 2, a sub 3, all the way to a sub n. If I multiply every term by r, so a sub 1 times r is here, a sub 1r times r is here, a sub 1r squared times r is here. So these terms when I multiply by r, they sort of, I'm moving them diagonally here, right? The power of r goes up by 1 every time. Right? Here it went from n minus 2 to n minus 1. Here it goes from n minus 1 to n. And then let me get rid of those arrows because they're a little distracting. And now what I'm going to do is I'm going to subtract the bottom from the top. So when I do that, of course, the a sub 1 comes down. But these things, when I subtract them, they're all going to cancel out until here. When I subtract the bottom, it's going to be negative. And so that's what this is showing right here. The left-hand side, s sub n minus r s sub n is here. And I end up with a1 minus a1 r to the n. And then I can factor out the s sub n, I can factor out the a sub 1, and then I divide to get a formula for the sum. To use this formula, we need to know what a sub 1 is, and we need to know what n is, and we need to know what r is to use that formula. So, what do I have here? I know that a sub 1 is equal to 3. To find my r, that would just be 6 divided by 3, which would be 2. And if I want the first 12 terms, that's telling me that n is equal to 12. So my s sub n is equal to a sub 1 times 1 minus r to the n all over 1 minus r. I want s sub 12. A sub 1 is 3. R is 2. N is 12. And then I get 1 minus 2. So I need 1 minus 2 to the 12th. If I take 2 to the 12th power, that's 4096. One minus 2 is negative 1. So I get 3 times negative 4095 divided by negative 1. So the negatives are going to cancel out, right? Negative divided by negative is positive. And I just get 3 times 4095, which is 12,285. For this problem, my a sub 1 is equal to negative 4. My r is going to be 2 over negative 4, which is negative 1/2, and my n is going to be 14. So I know s sub n is equal to a sub 1 times 1 minus r to the n all over 1 minus r. So s sub 14 is going to be a sub 1, which is negative 4, times 1 minus r is negative 1/2, n is 14, and then I get 1 minus negative 1/2. So that's negative 4. 1 minus, now I've got a negative number to an even number. That makes it positive. 1 to the 14th is just 1. 2 to the 14th, I can do on a calculator. That's 16,384. 1 minus negative 1/2 ends up being 1 plus 1/2. A little trick here, if you've got 1, remember I can just write that as something over itself. So instead of 1 here, I wrote it as 16,384. That was supposed to be. Couldn't read my writing. That's 384. Minus 1 over 16,384, and then 1 is 2 over 2. So this is negative 4 in the top. We get 16,383 over 16,384, and then divided by 3/2. It turns out we can divide 16,384 by 4, and that ends up being 4,096. So I get negative 16,383 over 4,096 divided by the denominator, divided by 3/2, but then that would just be multiplying by 2/3. And it turns out 16,383 can be divided by 3. That's 5,461. And 2, of course, goes into 4,096. So I get negative 5,461 over 2,048. Okay. So an infinite geometric series, if I have a sum like this, it just goes on forever. So this dot, dot, dot at the end, it never stops. We call that an infinite geometric series. Now for some values of r, as I add more and more terms, the sum gets closer and closer to a number we call the sum of the series. For other values of r, the sum either keeps getting larger and larger, or it oscillates between different numbers. It goes back and forth between different values. So in that case, we say a sum does not exist. So to determine whether an infinite series like this actually has a sum or not, we can look at this formula here. If r is between negative 1 and 1, then this value here, r to the n, gets closer and closer to 0 as n goes to infinity. If r to the n goes to 0, then the top will approach a sub 1 times 1 over 1 minus r. And that's just going to be then a sub 1 over 1 minus r. So that's the value for the sum of this infinite series if the r value is between negative 1 and 1. So this formula here allows me to calculate the sum of those infinite geometric series. It's not valid though if r is equal to 2 or if r is equal to negative 2. It would be okay if r is a half or a third or negative a half or negative a third or negative 4/5 or negative 9/10. As long as it's less than 1, then we would be okay here. So what about this infinite geometric series? Well, my first term is 1/2. My common ratio, well, there's two ways of doing it. I could take the second term and divide by the first term, or I could just say, how am I getting from one term to the next? How do I get from a half to a fourth? How do I get from a fourth to an eighth? I'm just multiplying the denominator by 2 every time. So my common ratio here is also 1/2. So A is equal to 1/2 and R is equal to 1/2. Since R is equal to 1/2, since 1/2 is between -1 and 1, then I can use this formula for S sub infinity. So that's just going to be A sub 1 over 1 minus R, which is 1/2 over 1 minus 1/2. But that's just 1/2 over 1/2, and anything over itself is 1. There's another way you can sort of see this. If I think of this square as equaling 1, then I can start and divide this square into 2 equal parts, and that side, of course, would be 1/2. And then I divide this into 2 equal parts, and that part would be 1/4. And then I divide this into 2 equal parts, and this part would be 1/8. And then I divide this into 2 equal parts, and that would be 1/16. And what happens, if I sort of imagine spiraling around, this, I can keep this up forever. And if I ever stop, there will be a little white uncounted area in the middle of the square. But if I imagine going forever, this spiral will take in the whole square, and that's where that sum is equal to 1. Sort of an interesting way of looking at that. What I've got here, my A is obviously 10. My A sub 1 is equal to 10. My R would be -5 over 10, which is -1/2. And that's also okay, because -1/2 is also between -1 and 1. So S sub infinity would be A sub 1 over 1 minus R. So A sub 1 is 10. We have 1 minus -1/2. So 1 would be 2/2 plus 1/2. So that's 10 divided by 3/2. Well, I can write that as a division problem, but then instead of dividing by a fraction, I multiply by the reciprocal, and we would get a sum of 20/3. Okay, in example 5 here, a tax rebate that returns a certain amount of money to taxpayers can have a total effect on the economy that is many times this amount. So how does this work? Suppose the government issues, let's say, a stimulus payment, right? Sort of timely here, so that each consumer has $1,200 more income. The government assumes that each person will spend some percentage of that, let's say 70%. So if I take 70% of $1,200, that's $840. So a typical consumer will spend $840 and they'll save the other $360 or pay off bills or something like that. So then the individuals and businesses who receive this $840 in turn spend 70% of it, or $588. But that creates extra income for other people to spend, and so on. Determine the total amount spent on consumer goods from the initial $1,200 rebate. Well, to see how this ties into what we've been talking about, essentially the first amount spent was $840. And then the next amount spent was 70% of that. Right, that's this $588. But what's going to happen next is that we're going to spend 70% of that. So I've got 840 plus 840 times 0.7 plus 840 times 0.7 squared, And at every point, I'd be multiplying by another 0.7. What I've got here is that a sub 1 is 840, and my r is equal to 0.7. So I can find an infinite sum if I just take a sub 1 over 1 minus r. So that would be 840 divided by 1 minus 0.7. That would be 840 divided by 0.3. And if I calculate that, that's then $2,800. So this original $1,200 payment to a consumer ends up resulting in $2,800 worth of economic activity. So that's more than twice the amount that was put out. If this percentage, 0.7, 70% goes up, this multiplier effect becomes even stronger. And that's how this kind of stimulus payment can actually have a pretty significant effect on an economy, which is sort of why the government tried to do that in this situation.